Welcome back to Math 103. This is video number 19 on growth and finance. How much is the investment worth in total at the end of the 6th year? We use the same thought process as in the 3-year example. We're investing $1,000 at the end of each year. Each $1,000 investment grows by a factor of 1.4 to a certain power, however many full years it's had the opportunity to earn interest. Thus, the first $1,000 sits in the bank from the end of year 1 until the end of year 6. That means it grows from $1,000 to 1,000 times 1.04 to the 5th. The last $1,000, as in the previous example, has no time to earn interest. It's invested at the end of year 6, and we're tallying up at the end of year 6. So it's just $1,000 with the benefit of 0 years of earning interest. Each of the intermediate investments of $1,000 has the benefit of growing some number of years greater than 0 but less than 5. Right? They're all represented here in the sum. We tally up. Yes, it's a whole bunch of plugging numbers into the calculator, and boy would it be nice to have a shortcut. And there will be a shortcut, but for the moment we tally up and we get $6,632.98. Great, that's just what it equals. We can ask, is this twice as much as the value at the end of the 3rd year? Is this twice as much as $3,121.60? No, it's more. This is greater than twice as much, and it makes sense that it would be. This amount right here is exactly what we computed earlier. This is the result of 2 years sitting in the bank plus 1 year sitting in the bank plus no years sitting in the bank. When we look at 6 years worth of making $1,000 deposits, we have the year 1 investment. This is the $1,000 that has sat in the bank the longest, and thus the first 3 investments have sat in the bank 3 years, 4 years, 5 years, so they're going to contribute an amount which is actually rather greater than what the last 3 years will contribute. So the final 3 years are the ones that sit in the bank for the shortest period of time, and they contribute less than the first 3 years, which have sat in the bank longer. Through laborious computation, we have tallied up the total value of the account at the end of the 6th year. All right, that's what it is. Is there a shortcut for computing the value of this long sum? What if we were talking about the end of the 20th year or the 50th year? It would be really quite depressing if we had to do this the long way. The good news is that yes, there is a shortcut, there is a formula. But before we get to the formula, it's very important to understand that the answer to the financial question posed here is a sum of solutions to distinct compound interest problems, several distinct problems. There's a separate compound interest problem for each $1,000 deposit. $1,000 times 1.04 to the 5th, that is its own compound interest computation. $1,000 times 1.04 squared, that's a different compound interest computation. So it's conceptually important that what we're computing here is a sum of the results of several different compound interest computations. Now let's see how that shortcut works. Let's work our way towards this formula that's going to save us a lot of work. Consider an annuity in which you deposit $2,000 at the end of each year into an investment account which earns 6.3% interest compounded annually. We'll come back later and deal with more frequent compounding. For the moment, we just have annual compounding. How would you write the future value of all your payments at the end of the 10th year as a sum if you kept investing $2,000 per year for all 10 years? Well, there are 10 separate investments here of $2,000 each. Each $2,000 investment is going to grow by some number of factors of 1.063, because the interest rate is 6.3%, and we're compounding annually. So there need to be 10 separate terms in this sum. Now here's an important point that causes a lot of confusion and really deserves some care. The highest exponent of 1.063 is 9, not 10. Now wait a minute, you ask, why is the highest exponent 9? when there are 10 deposits. So the first deposit, the very first one, is made at the end of year 1. That's what we're told in the statement of the problem. Okay, it's made at the end of year 1, and we're tallying up at the end of year 10. So from the end of year 1 to the end of year 10, 9 full years, and only 9 full years, have passed. So that initial $2,000 has been sitting in the bank earning interest for only 9 full years. Hence the exponent 9. You could also look at the last deposit made, the very last deposit made. That's $2,000 put in the account at the end of year 10. But we're tallying up at the end of year 10. So this $2,000 has had no opportunity to earn interest. What's the conclusion? There are 10 terms in the sum. The exponents of 1.063 range from 9 successively down to 0. So every term in this sum is 2,000 times 1.063 to the something. The somethings run from 9 down to 0, and that gives you 10 separate terms.